push back the extraction of I. That's all great. So what do you think? Is this necessary?
Here I have if I is not 0.
Exactly. So this already detects if I'm at the root. Does it detect this situation as well?
Yeah.
Yeah. So this means only continue while this is violated. So I really don't need those two lines, right? So we can eliminate them. It doesn't really matter for the asymptotic runtime of the algorithm at all, but it would matter for extra typing. It's one more piece of code I have to get right. Remember, a programmer introduces a bug for every 4 lines they type, and those 2 lines get you halfway to your next bug. Okay. So do we think this would work? What could we do to prove that it works? Depends on how formal we want to get.
We could just kind of make like a vector, right? Or like a...
We could try it, right?
Yeah.
Let's type her in.
We could. We could. We might in a minute. But let's suppose we didn't want to code it before we knew that it was correct. What could we do?
Can you just like kind of run through it with numbers?
We could run through it. Is that sufficient?
Probably not. Like
For our purposes.
For our purposes, maybe.
Yeah.
Okay, it's not. All right, so we should write a proof that this does what we claim that it does. And we haven't done this before. And this one's an easy one to prove, so I thought I would introduce you to that concept here. So if you're going to prove an algorithm, if you're given an algorithm, you have to do 2 things with every algorithm. You have to prove, first of all, that it does what you claim that it does, and it always does what you claim that it does. And you can't do that by testing it. Because for one thing, when you implement it, we'd have to somehow prove that your implementation was actually an implementation of this and not some other algorithm that looks really close to this. So you'd have to somehow prove the correctness of your code, which is a tricky thing to do. The other thing, though, is that you can't really exhaustively test all the possible heaps that this would ever encounter. So you have to come up with something else. And so the most common way to prove things about an algorithm is through the means of something that's called a loop invariant, which sounds terrible, but it's really not too bad. The basic idea is that we have a property that must be true before this loop begins, and then, or before this function begins, and then that property has to be true during the iterations of this loop, and then the property has to be true at the end of it. If it's true when this terminates, then that means that it does what we claim that it does. And so what our loop invariant is, as we enter the while loop, when we enter the while loop, for the while loop invariant, and you're going to see more about this in a later class in much harder context. So this one's a free one. So here's what a loop invariant looks like. We're going to say that that H, except for the newly inserted item, well, is a heap. Yes.
So the precondition has to stay true through all lines of code? Is that what you're saying?
Yes, as the loop runs.
Okay.
So the loop down there. So it has to, and then at termination, we want to somehow show that at termination, H with the new item is a heap. Okay, so let's kind of trace through this. And we're going to do this in a fairly loose way, but I'm going to give you the sketch of what a formal proof of this algorithm would look like. Okay? Just to give you that little nugget of how to think about this. So let's think about what happens when the algorithm is run for the first time. So for the first time, what do we know about H? So the first item we insert, what does H look like before?
It's a max heap.
It is a max heap, but I'm saying the first item inserted into the max heap. So the max heap would be...
The first item would be the largest, is that?
Well, no. So like, if I'm about to insert, then like this blank spot on my board is my max heap.
Oh.
What's true about it?
It's the root.
It's
empty.
It's empty.
Okay.
So first time, H is empty. So this means that this must be true vacuously at the beginning, right? So H is completely empty, therefore it is a max heap because there are no things in H that violate the heap property. It's also a min heap for that matter. Right? I always love those steps in any proof when you write out the vacuously true. It's sort of like all the elephants that I own are purple. It's true. I own no elephants, so unless you count the stuffed ones. Ooh, wait a second. I think there are some in my house. But if living elephants, I own none. Or you could have like all the birds on the moon are red. So, it's true. Because there are none. So this is true vacuously. It is the first time through. When we start, it's like that. So when we initialize the while loop, what we have is we have a heap where, so during the maintenance phase of it, so as the loop runs, it's also true for the same reason. So it's vacuously true. And then at termination, item is the only item in the heap. Hence, must be a valid heap. There are no children to violate anything. So now we know it's going to be true the first time that we run it. And then it's going to give us a valid heap. So from empty heap to a heap of one item, this succeeds. Now all we have to do is say, if we have a given item of any number of items in the heap, then we're going to have a heap at items n plus 1. So in other words, we want to say, if we have a heap, adding one more, this is true coming in. So let's say that we have subsequent runs. What have we got coming into the loop? So at the beginning of the loop, we know it's true because the first time run gave it to us that was true. And if we can show that it's true for an arbitrary position afterwards, it must still be true at the initialization time, right? So we're given a heap, in other words. So when this is initialized, this is true by what? By the H we are given. It's a little hand wavy, but not too bad. What happens next? How do we know it's true as the loop executes? So the maintenance phase of it, as the loop runs, so during the loop. Well, when does the loop swap with a parent?
When H sub I is bigger than parent.
So H sub I is bigger than the parent. It's the only time it swaps. Now, we know from before, so we know that the parent of I is greater than any siblings of I, if it has one, it might have one, we know that that has to be true. And we know that we only swap if H sub I is greater than parent sub I. Which means that if we swap, H sub I is the max of its parent and its sibling, which in turn means that the H sub I sibling parent tree that we generate has the heap property. Okay? So then, termination. When this thing is done, what are the two places that this might end up? So where might I go? Or where might this new item wind up? Are two stopping points. So we're percolating, we percolate up. What's the extreme end of our percolation? Once I hit the root, it might percolate all the way up to the root. So let's explore that possibility. So if the item percolates to the root, then what do we know?
It's the largest
How?
item.
So no, it's the largest one. How can we make the argument that it's the largest one?
Because it would only swap up to the top if it was greater than the other parents.
Mm-hmm. So we know from the maintenance proof we know it must be the largest. So the heap property holds. Right? Now, what if it doesn't? So otherwise, if we stop somewhere in the middle. So we stop if a swap would invalidate the heap. Hence it must hold. It's not airtight. If I was going to write a technical proof in an upper division course, I would write much more than this, but it comes close. It's not too far off. But we know from the standpoint of doing this with just one heap, one item, and then doing it with just adding an arbitrary number of items afterwards. Now, I didn't quite prove all of that, but I've come close to building an inductive proof that that invariant will hold no matter how many times I run the algorithm. Hence, this algorithm is guaranteed to give us the correct result. Just coding it up and trying it doesn't do that. So we have to do that part. We know it's correct now. Now the other thing is we need to know how efficient is it? How much time will this take to run? So how long does this operation take? The inserting and then getting the size.
Or inserting the vectors constant time?
Yeah, we can pretty much call it constant time. It's not quite, because every now and again the vector will have to double its size or double its capacity, but it doesn't do that very frequently. So in a very roundabout sort of way, we can call these things constant time operations. All right, so we can say that these are big OI operations. What about this? How many times might that loop go?
The depth of the tree.
The depth of the tree, yeah. So we only consider the parent. So we only compare to parents. So this is a maximum of the depth of the tree. And the depth, so if we have n elements in the heap, including the one we've just inserted, what would the depth of the tree be?
Is it 2 to the n?
No. It involves exponentiation somehow. But
Was it log
Yeah.
base 2 to the n? Or log base 2
log
n?
base 2 of n.
Yeah.
We usually write LG in for the log base 2 of n. So that means that this thing would be log n, which means that the total runtime of this algorithm would be in big O1 plus big O1 plus big O log n. And of course, the only thing that's going to dominate that is going to be log n. So because the constant times will go away. So that means that the insertion into a binary heap takes place in logarithmic time. It's very efficient. We can do better than that, but it's otherwise very efficient. Actually, we can't do better than that on insertion, but there is another kind of heap that can do better on extraction and rebuilding. It's called a Fibonacci heap. You'll see that later, towards your senior year maybe, if you take a theory class. Or if you just get curious when you go home tonight and type Fibonacci heap into Wikipedia, it will show it to you and give it you implementations in like 12 different languages. But if you go out on the wide internet, you can find tons of them. Yes. Did you have a question? Oh, you just read it. Okay. Okay. So now we know that this happens in log time. What about extract min? Or extract max, rather. So first thing we need to do is extract the maximum element. So where's that going to be at?
Be the front of the
It's
vector.
going to be at the root. And we're going to assume in our algorithm that the user of it is going to play nice and not give us an empty heap and say, give me the maximum of this. If we say fault in that situation, it's their fault. That's what we're going to say. So we're going to say the max element will be equal to, actually I'm going to call this the result because this will confuse us later on if I don't do that. So I'm going to call it result will be at H0. And now I need to swap with the end. Okay, so now I did push this over to the end of the result, right? The end of the vector. So how do I do that? Where was the last inserted item at?
Be at the end of the.
Left to right, bottom level.
Mm-hmm.
Yeah.
Yeah, so that's really just going to be the end of the vector, right?
Yeah.
The last element of the vector was the last one that was inserted. If you look, it's always pushed back, right? So the back will always be the last element. And I can actually get that. I could say that I equals H, or H dot size minus 1. And now we're going to swap H sub 0 and H sub I. So we're going to swap those two. Well, what do we get? So what do I do next?
Oh, you check to see if the thing still holds?
Well, the first thing I need to do, though, is I need to erase that last item. How do you erase the last item in a vector?
Pop or. Oh.
Does a vector have a pop back?
Doesn't.
I think it does.
I think it does, yeah.
So we'll pretend it does.
I'm pretty
If
sure
it
it
doesn't, we
does.
could always like write something that does that, but we'll do a pop back of H. And so that's gone. And now we percolate downward. Okay. What would the stopping conditions be for percolating downward?
Your array is empty.
No.
Where do I know there's no need for me to percolate further? It's either where the property holds, or
You have no children?
I have no children, so I stop at leaves. So why don't I say that I have an imaginary function called isLeaf, and it will take H and I. Really, this is really simple. If I take 2I plus 1, and that is less than the size of the vector, or less than the size minus 1, then that means there are no children there. So that can be done in constant time.
Leaves are nodes without children, right?
Correct.
So you couldn't just, if you're looking for the most recent insertion, you couldn't just go to the level above that? And go from right to left?
No, it'd always be the one at the very end. Because remember, the vector is stored in row level order.
Right.
So the rightmost one of the bottom row will be at the very end of the vector.
Yeah.
I'm guaranteed that.
Okay.
Because I always insert at the end of the vector. Right? Think about it, the vector goes across. So the next available slot is always right at the very end.
Okay.
And if it needs to start a new row, that happens automatically too, because that would be the left-hand child of the one above.
So are you saying that when it gets to the root, it will stop?
No, I should say while not is leaf.
Okay.
Yeah, there we go. Sorry. So while it's not a leaf, and well, it's going to have to be one of the smaller. It's going to have to be smaller than one of its children, right? So and actually not I. I need to set I equal to 0 right here, and now it can be I. So I'm going to start at the root. I'm going to percolate down from there. So while this is not a leaf, and H sub I is less than the left-hand side, or the H sub left, or H sub I is less than H sub right, now it's assuming that it has this. We'd have to have some kind of way to check that it had that. Then that means I need to swap it to the most extreme child, right? So now to swap to the most extreme child, I need to find out what that is. So if H at left of I is equal actually there's a better way to do this too. I'm going to write this in a better way. This way is going to get kind of ugly when we try to implement it. Let's think about this another way. I'm going to look at my current node, I. I'm going to start there. And what I'm going to do is I'm going to find out, of the 3 potential nodes that are around us, which one is the biggest. Okay, what's the index of the maximum one? And so I'm going to assume that, well, let's see. Let's do it this way. So I'm going to say, I'm going to have some kind of a condition up here. I'm going to make that condition be while not done. So maybe up here I said done equal to false. So while I'm not done, then I'm going to do the following. I'm going to say if, let's say that I've got my left is equal to the left-hand child of I, my R is equal to the right hand of I. So then if L is less than H dot size and H sub L is greater than H sub I, then I'm going to say that the max index is L. And then if R is less than H dot size and H at R is greater than H at max, so I assume that I was the max the first time around. Now I'm going to say if I found something bigger than what I think is the max, then it's the new max. Then I get max equal to R. And then down here, if max equals I, done equals true, otherwise we're going to swap H sub I, H sub max, and I'm out of room down there, but we're going to say that I is equal to max, and we're going to repeat the loop. So that finds the most extreme child and pushes it downward. Would you agree that that would work? I'd find the biggest of the three that way. I assume it's I. If L is bigger than that, I said I should really do like max equals I up here too. Maybe it would be less confusing if I did it this way. So max equals to I until I find a counterexample. And then otherwise I'm done. I'm done if there isn't one. And then if there's not, then I have to do that swap, and then I have to start comparing there. I know that the maximum is going to be the biggest of that little subtree because I know that if it was the left-hand child, the left-hand child has to be bigger than the right-hand child. And if it's the right-hand child, then the right-hand child has to be bigger than the left-hand child and bigger than I. So that will certainly swap it in a way that percolates things toward the bottom. And it will do so without overrunning the end of the vector. The proof of it will be about like the proof of that one over there, because if I look at this, I'm always swapping in a position so that the subtrees always maintain the heap property, and once I reach the leaf, I must have the heap property still intact. And because this was a heap to begin with, I know that everything is where it should be. So now we need to work out the runtime of this. So these things are all things that take place in constant time, right? So this is constant time. Each one of these things is a constant time operation, right? There's nothing in there that's more than constant time. So that means that this loop, how many times does it go? it also goes through the depth, right?
Yeah, log in.
So this would be O log in, which means that this algorithm is also log in, which means that any of these is log in.
Would the original way you were going to do it would have been less efficient?
No, it's just been more writing.
Oh, okay.
Let's see if we can implement this. Let's see if it actually works. We've proven it's correct. We don't know that it works yet. It's a classic joke from Donald Knuth. You know who Donald Knuth is? Ooh, okay. I got to introduce you to Donald Knuth, and then we'll code this up. I actually got to meet him once. So he's a famous computer scientist. So, that's for how much fame that buys you. But he's a computer scientist at Princeton, and he's retired now. He still gives what he calls his little talks, and they're just lectures that he comes up with every now and again for his current research or things that he finds interesting. And then he'll go and he'll give those at Princeton. And I was really lucky once when I was out near Princeton. It was like 30 minutes from where I was. And then I saw on the internet that he was giving one of his little talks. I'm like, ooh, sweet, I'm going to go to it. And so I went. Then I walked in just before he began, and then he asked me if I was a student at Princeton, and I said no. He said, how'd you find out about it? I said, I randomly saw it on the internet. He said, oh, good. So you might even be able to identify which one I'm at, because he made a comment about that at the beginning of his talk. Anyway, here is, let me find a picture of him, because that will help you understand it better, I guess. I don't know. It'll make him seem like a person. So, this is Donald Knuth.
Is he the one that created C?
No. C was created by Dennis Ritchie at Bell Labs.
He couldn't have created
He has a
C. He
beard,
doesn't have a
right?
beard.
He doesn't have a beard, yeah. He never wore a beard, to my knowledge. So this is about what he looks like now. He's in his 80s now, I think. Actually, I was on Wikipedia. If I press back, we'll find out how old he is. 81, yes.
Oh, the art of computer programming, yes.
Yeah, he wrote The Art of Computer Programming.
Volumes.
So he decided that he would write a book called The Art of Computer Programming, where he would give you all the basic information you needed to be a computer programmer, including algorithms that you must know and techniques that you need to know. And then after you got about halfway through writing what became the first volume, he realized this was going to be multiple books. And so he targeted it at 7 books, and so he wrote 3 of them and then stopped. Now, that was back in the late 60s. So the first edition was written for a typesetting system on a DEC TOPS 20 system. He resumed writing in the late 70s, and the typesetting system that he had used was gone. It couldn't be found anywhere. There were no more TOPS 20 computers in operation. And so he actually wrote a new typesetting language so that he could continue working on his book. And that new language is called TeX. And if you take Leslie Lamport's extensions to TeX, it becomes a language called LaTeX, which is what most academic papers are authored in. So he's the creator of TeX and by extension, somewhat of LaTeX, which LaTeX is really just a set of macros that makes TeX easier to use. So like if all of you are probably going to be so inspired by all this that you're going to go on to get a PhD, you'll spend a lot of time writing documents in TeX, right? If you don't get a PhD, never knew you. No. Just kidding. A PhD is not something to be entered into lightly, or indeed at all. But I can tell you from experience, it's rough. But he wrote that language, and then he continued typesetting his book, and he retypeset the first 3 editions, and he fixed errors that were in it. And then he set out to write the 4th volume, which he's been at for the past 30 years now. And there is a thing out there that his publisher is calling the 4th volume, but he's not real sure that he's going to call it the 4th volume. So he originally released the 4th volume a bit at a time and addendums that he called fascicles. So you can buy volumes 1 through 3 and then 7 fascicles, which now come bound as a unit that is called the 4th volume. It's a really good book. You should get it and you should read through it and work through it. It'll take you a few years to get through all of it. But it's really good, and in fact, you can actually achieve maximum. You can have an optimal reading experience because in the first volume, he gives you an algorithm that you can follow to get the most out of the book. And if you follow the algorithm, it works. He also was a progenitor of what's called literate programming. If you ever heard of that before. It's kind of a forgotten. So one of my colleagues at Maryville College, well, my only colleague at Maryville College, refers to it as, it's not true, I got other colleagues. My only computer science colleague at Maryville College refers to literate programming as the lost agile method. So the basic idea was, instead of writing programs in a way that a computer can understand it, we write them in a way as if we were explaining them to human beings, and then they can be processed and turned into computer code. And so when you read a literate program, it reads like an essay that's explaining all of its algorithms, it explains how all the pieces work, and then all the pieces can be assembled into code. So like there's C code embedded in it, and then, or whatever language you want to do it, and then you make a human readable version that is nicely typeset in LaTeX, and then you make a computer readable version, which is a bunch of C code. And it's a really neat technique. In fact, he also wrote a 7-volume set on typesetting called Computers and Typesetting. And I think it's volume 4 of that 7-volume set is the tech interpreter, the tech compiler written as a literate program. And it's actually quite readable. In fact, I read that and I understood how to use tech better as a result of it, which I can't say that's true of any other thing that I've ever encountered where reading the code clarifies the use of the code. So anyway, that's Donald Knuth. He is a legendary figure in computer science, and he's one of, might call him like a second-generation computer scientist, because he's a little bit younger than the first generation, but not by a whole lot. So he's kind of a contemporary with Edgar Dijkstra, and Edgar Dijkstra has already died, but most of the first, I think all of the first generation is gone now, because they would have been active in the 1940s. That's just too long ago to have been doing computing and still be alive now, with a couple of exceptions. Who among you have had the architecture course, the assembly and architecture, or the organization? So you've had the organization, right? You're in it now. Have you done Carnot maps? Carnot's still alive. I was amazed by that because the Carnot map paper was published in the 1950s.
Oh, wow.
But, let's see if I can find it. Maurice Carnot introduced it in 1953, but he is still out there. He's 94 years old, but he's alive. He still gives lectures every now and again. I've tried to catch one, because time's probably running out for that, but I haven't managed to catch up with them yet. This is the neat thing about computer science. Most of our founders are either like very old and still alive, or they didn't die that long ago. Or they died extremely young, too. Like the real founders had a tendency to commit suicide. But like Alan Turing, he killed himself. As did Kurt Gödel, killed himself, sort of. That wasn't his intention. So, Kurt Gödel always had this perpetual fear of the Nazis. And it probably has something to do with that when he was a PhD student, the Nazis killed his advisor. And then said, we're going to round up the students of this advisor, and so he fled to the United States. So that would give me a healthy fear of them, too. Well, in his later years, because he wasn't young when he died, he was in his 70s, he started to go a little bit senile, and he decided that they were going to come get him and finish him off. They were going to finish the job they didn't manage to do back in the 40s, and they were going to do it by poisoning his food. And so they basically humored him on this, and his wife humored him on it and said that she would go away to a special poison detection class and learn how to taste his food to see if it was poisoned. And so she did that. She would taste all of the food. She'd take a bite of each food, each item on his plate, and say, yes, this food is okay. And then he would eat it. Well, then she ended up getting hospitalized for an illness for about 4 or 5 weeks, or it was more longer than that, but I think it's about 4 or 5 months, actually. And so during that time, he didn't eat. And so he starved to death. So, yeah. Yeah. Mathematicians they'll usually live a very long time, or they will die in a somewhat tragic way. I'm serious, look up mathematician deaths. They really like sometimes play into that 27 club thing, like around the ages between 27 and 45 are dangerous years for mathematicians. I say that to myself, if I can make it to the next 7 years, I'll probably live to be 90. So anyway, that's a little diversion here. Okay, so let's see. But he had the whole point of that whole bunny trail was, Knuth said some code that he sent to someone. I've proven that this is correct, but I haven't yet tested it. So be very cautious with this. So we're going to try it out, see if we can make this work. And I'm actually going to implement this in a very generic sort of way, because the only difference between a min heap and a max heap is which direction the alligator is facing. Right? So if I wanted to turn this into a min heap, then I would just flip him around and it would become a min heap. It's really all there is to it. Oh yeah, and I would also call extract max, extract min. That would be the other change that I'd make, and I would flip around these signs as well. So I'm going to do this by using a function pointer. So I'm going to pass in the function that will validate the heap section. So I'm going to write heap insert and heap extract. And so I'm going to provide you with the generic heap that can be used for either rule, or for any rule that you might want. Okay, so let's do this. We're going to have heap.h. And so we'll have the file will be heap.h, and its purpose will be the purpose of heap.h will be the, what do we want to call it? It will be a template of a generic heap. Oh, that's the other thing. It's going to be a template. Because you might have a heap of something. Okay, so what we'll do is we will have I'm going to do it as a class. And the class will just be called heap. And it's going to be a template, like I said. So it's going to be template, and then I'll have class and heap. So a template class will have public, and we'll have private. Now the things that we're going to have that will be private is we're going to have a vector of type t, right? And this will be called, I'll call it _h, so it lines up with my algorithm over there. And then I'm going to need the property function. So I'm just going to call this valid. And this is going to be a function pointer. And it's going to be a function pointer that returns bool. So it's going to be bool, and then star, and then I'll call it valid. And it's going to receive a const reference to so it's going to receive a const reference to a parent, and then a const reference to a child. And so we'll just apply whatever heap property we want. Okay, this is wrong though, because of the way that function pointer declarations work. It's going to be like this. I'm not going to do a templated type def, so I'm just going to manually type out that whole thing in the 2 times when I'm going to want this. So when I construct a heap, I'm going to need to provide, in the constructor, I'm going to need to provide a bool star valid const ampersand, comma, const t ampersand to do this. So that's my constructor. And also go ahead and create a copy constructor, because we should always have a copy constructor. Now I can't have a heap without a rule, so I'm not going to make a no-arg constructor. So we have to provide it with at least a function to do this stuff. And so I'm going to have a heap bool, or not, sorry, I'm going to have a heap const, and then heap ampersand right hand, or I'll say other. There we go. So we'll just copy the valid stuff from the end, all that kind of stuff from the other one. I'm also going to go ahead and say we should really have something that can convert a vector into a heap. So a heapify operation. So a heapify, and that's really what the function is called. It's called heapify. So I could have a heapify, and if I'm going to do that, I should have this constructor here. And then I'm also going to pass in a vector of type t, or a vector reference of type t. I'll go ahead and make it a const vector reference of type t. And that, I'll call it list, or I'll call it v. Yeah, I'll call it v. There we go. So I want to call this, I'm just going to call this h. I'm not going to call it underscore h. I'm not going to provide direct access to those. All right, so there are my three constructors. So I can heapify from a given list. So we're going to have the heap methods, and so the heap methods will be insert. So we'll have void insert item, and so we're going to have a const t ampersand reference. Or actually, I'm just going to const t ampersand. And that's going to be my item that I'm going to insert. And then I'm going to have something that returns something of type t, which is going to be, I'll call it extract. Because I don't know if it's going to be a min or a max, right? So it's going to be my two fundamental heap methods. So I'm wrapping the whole thing in a class just for convenience, because when I use this, I just want to be able to tell it extract or not. But I'm going to implement my binary tree inside of this vector down here, because like I said, it'll be a little bit easier. If I didn't do that, I would have to keep track of where my next available slot pointer was, and that's a little tricky to get right with the pointer implementation of a tree. So if I was going to do this, even I do know how to do that other one, and you could work it out for yourself how to keep track of where that next slot would be. But actually, you can do it by traversing, and if you do it by traversing, it's still log time, but it still wastes time. If I was going to implement one of these in the real world, I'd implement it like this. That's what I'm getting at. So this is the way that I would do it. I would use the array representation, or especially the vector representation of it, because that's quite nice. Okay, so I'm going to go ahead and copy these things down here. So let's work on our constructors. An awful lot of typing for this, which is going to encompass this arrow valid equals valid. There we go. This one will be ever so slightly more complicated. So this will be, this creates, I'll just make a comment here, this create an empty heap. And then this will heapify a vector, which is a handy thing to be able to do. Okay, so if I'm going to heapify my vector, how would you go about doing such a thing? So I've got a vector. I want to put all of its elements into heap form. Of course, I'm also going to go ahead and do that valid business. I'm going to go ahead and say that I'm going to use my other constructor, just because it's good practice to use a constructor that already does what you want. So I'm going to use my other constructor, but then inside here, I need to heapify. So heapifying is very simple. All I have to do is go over the list and insert them all into the heap. So we are going to heapify. So for auto ITR equals, and I'll say v dot begin. ITR does not equal v dot end. ITR plus plus. And then I'm going to insert star ITR. Done. Okay. So then, how long will that take to run? What's the efficiency of insert? Make a little comment here. This was big O log n. Right? We did that already. How many times will that for loop run?
Size of the vector.
Size of the vector, so it's going to be n log n. So it takes n log n time to build a vector, to build a heap from a vector of n elements. Not too bad. Fairly efficient to put one together. Let's then go on to the next constructor, which will be super simple. We're just going to copy the others valid, and then we're also going to copy their h. And then left click. And of course we need to put our template arguments in here. There we go. So we've got our constructors. That just leaves our insert and our extract. I'm going to copy my label too with that. Okay, so for insert, so we're going to do a heap insert, and so that's going to have a template class T.
Template?
Yep, template. Template, there you go. It's late in the evening, what kids expect. This was a programmers are supposed to be on their in their prime, right? Half dead from sleep exhaustion.
Right.
Sleep deprivation. And you're like, yes, I can code. I've become one with the machine.
Creativity peak because you lose those filters.
That's right. The deadline's coming near that makes you a super coder as well.
A little bit of extra pressure.
Yeah. All right. Actually, I remember teaching a software engineering course, and I asked what are the 5 phases of software development, and they said denial, anger, bargaining, depression, and then acceptance. But I was like, I can't say that's wrong.
That's so funny.
I remember I about fell out of my seat laughing when I read that. But anyhow, we're going to insert an item, so we're just going to implement this thing over here, right? So insert max, we're going to start out by pushing the item onto the back of the vector. So I know I'm going to have like an I right here. And so we're going, and I should go ahead and implement, for my heat methods, I'm going to go ahead and throw in some preprocessor directives here. I'm going to do a left. So left I will be set up to be, well, remember that would be
2I plus
2 times I plus 1, putting parens around it just because I don't know what expression is going to be there. Right of I will be 2 times I plus 2. And then the parent of I will be, remember that was I minus 1. I minus 1 divided by 2. No semicolon. There you go. When you do those pound sign defines like this, it's basically like doing a search and replace. So imagine yourself going through and finding all of the places where I type right in all caps and then replacing it with that pattern. If I put a semicolon there, that would be bad. It'll let you do it though. It'll let you put any text over there that you want. But anyhow, I've got pound sign defined left, right, and parent, so I'll be able to do those operations in an easy fashion. Fashion is not going to be error prone at all. So I've got int I, and then I'm going to do a pushback, right? So we're going to push to the next slot in the heap. So then we're going to do and I'm going to make a comment up here too that this is big O log n. So we're going to push to the next item in the heap. So next slot, so that's h dot pushback, and then I will be equal to h dot size minus 1. And then after that, we're going to do our while loop. What does our while loop say? So it's going to be while. What's the first part of the condition?
If I is not 0.
So it's I does not equal 0, and
H of I is greater than H of parent I.
right, h sub I is greater than parent I, but really what I want to do is I want to validate, right?
Validate.
So then I will say valid, and then I need the parent first. That's the way I made the function work. And h sub I. Now we need to swap these things. How do we do a swap?
Swap.
You can include algorithms.
We can include algorithm, we could use the standard swap. Or I can code it up with 3 variables. I'm going to use the existing one because that's just faster.
Yeah.
Right. So standard : swap, and I'm going to swap h sub I with h sub parent sub I. And of course, it doesn't matter what order I put those in. But here we have it. So that will percolate. And before I forget, I'm going to go up here to the top. I'm going to do a couple things. One is I'm going to put pound sign if and def heap underscore h pound sign define heap underscore h. And I'm also going to include vector, and I'm going to include algorithm. Now I've got those.
So I have a question. So when you're pushing that, are you pushing that to the vector that is like the private data? Or
Yes.
So wouldn't you need like to do like a this for that? Like
You don't have to, and you don't have to do that unless you've shadowed the parent, or shadowed over the local variable, so it's not ambiguous. I could put this arrow h in front of it, and some people will all the time. I only do it if I have to. my typical style. Some people do it all the time.
Oh, and I think you called that underscore H.
Did I call it underscore? I think I deleted the underscore.
Oh, did you?
Yeah, because I decided that I wasn't going to be using them as parameters or
Ah.
anything, so I didn't want to
Yeah.
type underscore.
Gotcha.
Okay, so we've got that, and we see how that I'm using my validation rule, so this is a generic heap. Right? So now I'm going to do a heap extract. I find the item in O one time, but it takes O login to rebuild. So template class T void colon extract, which I think already had the extract on it, and it's not void either, it returns something of type T. Alright, so I'll have my extract right here. So what's the first step in extract? I'm going to get the result, right?
I is equal to H dot size minus
Yeah.
1.
So the result is going to be
Oh, H of 0.
H sub 0. And then after that, now I've got my I.
9.
What's that? What's next after that?
H dot size minus 1.
Is that the next part of the algorithm?
Oh, then we're swapping H and I.
Right. So then I'm going to do standard swap on H sub 0, H sub I.
H dot pop back.
Oh yeah, pop back.
Are you asking because you can't see it over there, or?
Yeah, I can't. It's like, I could barely see it when I was over there with it in the background. So H dot pop back. I want to make sure it lines up with it. So this is going to be, oh wait.
You had the pop back, yeah,
After the swap, yeah. Technically, there is a little bit of something that I should do here.
What's that?
I should make sure that I'm not doing the pop back on, or I'm not doing the swap if it's empty. Right. So, in other words, if H sub 0 was the last item, well, I guess that would still work. So it would just swap with itself and then pop, and then it's done. So yeah, that'll work. I probably should put a check right here for that. It's like stop if it's empty. So if H dot size equals 0, we're going to just return the result. So we're going to remove the result, swap the bottom off the top. And now we percolate, right? So what's my percolation condition? I've got done. So bool done equals false. And then I set I equal to 0. Is that right?
Yes.
Okay. And now I've got my condition while not done. So while we're not done,
L equals left eye. R equals right eye. Max equals I. If L is less than H dot size and H of L is greater than H of max.
so what was it? It was if
L is less than H dot size and H of L is greater than H of max, then max equals L.
now really I shouldn't say max. I'm gonna change up some words here. Okay, so one thing I haven't declared it yet. I didn't have to do that in pseudocode. It's gonna have to be T, and I'm just gonna say extreme. declared it right there. So we're going to find the most extreme. They'll have if R is less than H dot size. So really this should be and. So to find if L is the extreme, then that's really saying that it should be the one that's in the slot that I currently occupies, that the max currently occupies, right? So I could say this. I could say and not, and then we'll have valid, and then that will be H sub, let's see, max, followed by H sub L. In other words, if L is not subservient to the or to the extreme, then that means that the extreme is L. Right? Otherwise, if R is less than H dot size and not valid, H extreme, H R, then the extreme equals R, not 4. R, that would have been a fun one. Why is it always putting this in the fourth element? Okay, and then down here, after we found the most extreme, if max equals I, or extreme equals I, then we are done, right? So if the extreme is equal to I, so see if we are done. Done equals true. Otherwise, we are going to do our swap. So we'll do a standard swap for H sub I and H sub extreme. And then we'll just keep on doing this for as long as we need to. Once we're done, and then I can return the result. Right? A couple other things I'm going to add. I'm going to add some generic stuff. Let's see, bool empty, which will return true if this is empty. And then I'll also throw in an int size so we can determine how many elements there are. Excuse me. These will be boring though. So let's just go ahead and put those. They'll just make it handier to use. Actually, I'm just going to return each dot empty. Now I got to do all this typing for the template stuff. There we go. And then for size, there we go. All right, so I think that's all my methods there. Let's see if I can use this. I'm going to do a maxi, and so I'm just going to ask for a series of integers, and then we're going to do extractions until they're done, and that will tell us if it works. Okay, so let's do a maxi. We're going to implement a maxi using our generic heap. With IO stream, I'm going to dot H. And then I'm going to do using namespace standard. And then we're just going to get some numbers. So I'll do like cout, enter numbers, enter the non-number to finish. So I'm going to have a heap H. Now I need to have a validate function, right? So I'm going to have a rule, and I will call it max valid, and that will be, I'm going to have a type integer, and that will be the parent, and an integer, and the child. And so in a max heap, what makes a max heap valid?
Parent is larger than the child.
Parent is greater than or equal to its child, right? So I'm going to say parent, so we're going to return parent greater than or equal to child. Done. And then in here, this needs to be of type int. And then I need to pass it my max valid function. So now it's going to be a max heap. Okay, so we're going to insert the numbers. So we'll do while cn_num. Then I'm going to do h.insert num. And then we're going to extract the numbers. Okay, so we'll cout, and then we'll do extract max. And then we'll say while not h.empty, cout h.extract, and a space. End of all that, I'll do cout indel. And that's it, right? So if my max heap works, this should work. Now I used some C++11 extensions, so I need to make sure that I compile with the C++11 standard turned on. Okay, so when I go out of here, I need to do g++ -- standard equals C++11 max heap.cpp, and then -o max heap. I would have been surprised. Okay, no matching call for vector pushback. That's interesting. Let's see, what did it, okay, so, oh, I had an unterminated if and def. So that might have some bearing on things. So down here at the bottom of this, I need to do pound sign endif. Oh, I didn't declare L in the function down there. Let's see what this is complaining about here. Vector does not name a type, so I got some places where I've got a vector without a standard in front of it. Okay. And then down here in this function, I just started using L's and R's without first declaring them, so maybe I should declare those. No matching function for standard vec. That's error. Vector does not name type. I did it down here too. To make sure they got everything right up here. Yep, that's good. Invalid conversion from bool star int to bool star const int ampersand. Oh, okay. I didn't adhere to what I said my standard was. It should be const int references. no matching function. Oh, you know what I didn't do? I get it now. When I did pushback. That's not there, it's in the other. I didn't put the item in parentheses. Whoa. Being compiled. Anyone care to place bets on whether this thing's sync phones?
I'm gonna find Monopoly dollars.
All right, let's give me some numbers to put in here. 15,
7.
7,
42.
42,
I was thinking
11.
What was I saying?
Anything else?
117.
117, 25,
4.
4,
11.
87.
87. Just put in some 0 and like a -1 for good measure.
There we go.
All right, I'll put a period at the end, and that should do it. And it extracts. Did it work? Not quite.
Huh. Interesting. Interesting selection.
I mean, it kind of works.
It kind of works.
It moved him.
It moved.
It did move him.
Swap them around. and stuff.
I was about to say
It did a thing.
they were swaps.
Swap it.
It did it.
So the swap function does work.
That's good.
So let's go back over here and take a look. So first of all, let's look at insert. What I did not do,
What did you not do?
I didn't update my eye.
Oh, that makes a difference.
Yeah. So that needs to be updated to the parent of I, because otherwise it swaps and everything's cool, so we're done. So we made it through one swap, hence we did do a swap.
All right.
All right, let's try it again. Oops. So we'll compile it and run it. I'm going to do something easy. 1, 2, 3, 4, 5.
1187.
And we got 1, 5, 4, 3, 2. We're getting warmer.
Yeah. Why did not get that first one though?
Extracted it first.
That's the question.
Not while it is valid, while it's not valid. Right? So we do the swaps for not valids. All right? Again. Hey. All right, so let's try one in random order. So, oh, darn it, I've lost my command now. There it is. All right, give me one. 27.
4.
4.
98.
98.
777.
777.
Is it an unsigned int?
It's assigned in.
343.
Darn.
What are we? -1, -23, -8,
1187.
11d7, 9. And I was going to end it there.
Huh.
Darn.
It started doing it.
We were so close too.
Well, it did extract the biggest one. But that means there must be a bug in the other one, right? And I bet you I forgot to update my eye in that one as well.
Is it register?
So if we come down here, yep, look at that. See, I swapped, but I did not change my eye.
Nice.
So it would only make it down the tree one position. And then it would just think everything was great. But everything wasn't great. All right, 777. 1, 34, 9, 1024. -1. Give me some numbers.
Million.
1 million.
You had to say it.
Negative 57.
Negative 57.
7.
666.
Let's see what we get. Hey.
Hey.
Hey!
Yay, we've done it.
Let's crack open that champagne.
Yes, over our heaps. Let's make a min heap.
Heaps of numbers.
You got one done correct?
The min heap will be very similar to the max heap.
You just need to change the function to the start.
Yeah, there's a few places where it says max, and I probably want to make it say
You're the homework at worst.
Did.
here. Actually,
Or I don't know, I guess, but how many questions are there? Oh.
Okay, so the mins are taken care of.
Depends on each one.
And in the min valley,
Flip the crocodile.
we flip the crocodile around. He's eating the smaller fish now.
Oh,
Smaller
that,
swim.
that looks the same. So like 5, 6, 7.
Yeah, you're 10, 20, got a really blessed.
And I should say that this is extract
Oh,
min.
it was 15 on that, huh?
Yeah. If this is right. What's your measure?
Computer engineering.
Yeah. Everybody's computer science.
I know, I don't need it.
I'm like dual majoring, computer and electrical proficiency. Or so close to it.
Might as well. And then minor in math. You can only take 1 or 2 extra.
All right, so let's give it something to play with.
8.
Oh, numbers.
27.
27,
That's hard.
but negative 1.
They have to be whole numbers, correct?
Yes.
If you fed it a double, would it freak out or would it just cut it off?
That would cause it to terminate, so that it would stop the list there.
4.
But 8, 6, 7, 5, 3, 0, 9.
Ah!
4. 40.
I've been on 4 this whole time and you're just going to take 4 from me?
1080.
10, 8,
1080.
10, 80, okay.
720.
2K.
720.
360.
180.
Like 144? Would that be?
2070. 52.25.
22?
52.
Ah.
What are their phone numbers other than songs? Well, there's another
We
one.
covered the best one.
Oh, there's
Wait,
a.
what
There is
about-
anybody really has that number.
What's that?
What if anybody really has that number?
Yeah, that is a valid number, and usually people get that number. They're really grumpy when people call it. I know because I've called it most of the area codes in the country. Did not find a single Jenny.
224
224
5972.
5972. What's that from?
That was Donald Trump gave out Senator Lindsey Graham's phone number.
I bet that's not Lindsey Graham's phone number any longer.
Nope.
That's good. Okay. Trying to remember the song. There's another song that has a phone number in it.
Was the stainless steamer?
It was like from the, I want to say it's from the 60s or 70s. This is important. We gotta figure this out.
6, 7,
Google.
6, 7, 8, 9, 9, 9, 8, 2, 1. Wait.
What song are you putting?
This is from like a Soulja Boy song. Oh,
No, this is.
Oh, that's just because of how
Yeah. 6, 7, 8, 9.
Soldier Boy, really?
Yeah, dude, that
Listen,
was
Soulja
like
Boy
in the
is a
vibe.
he's a
Soldier Boy is.
he's a 2000s icon, alright?
Literally though.
He has like custom.
He has like 3 hits.
Yeah, but he actually is quite the entrepreneur. He's like worth like $40 million.
Goodness gracious.
Yeah, you can buy
Well,
like
I'm-
5,000 different versions of consoles that you like. You would change the exterior.
Goodness gracious. That's too many, in my opinion.
I'll see if I can find it.
Doc's on a mission.
Yes.
I want to listen to that song.
What, 86753 now?
No.
Soulja Boy?
The Soulja Boy song.
was at a party and they were playing Soulja Boy, and I was like, come on now. I could see there's some Soulja Boy hits, certifiable bops, but they don't have a place in 2019.
Go southbound, maybe.
6345789. It's Wilson Pickett. That's the name of the song, actually.
I don't have any SD cards.
Before my time, I think.
It's well, mine too, technically.
Yeah,
So it's
I
just
don't
the
know
six
my
that's
Wilson
displaced.
Pickett.
I guarantee you know one of the songs that he did.
Maybe.
Land of a Thousand Dances was his song. It's played it by like every brass band ever.
Yes.
At football games.
Mm.
But that was one of his songs. So yeah, that has to be like 70s, 1970s. It's the lyrics of the song, he's basically running a hotline that you can call in if you're lonely and talk to somebody. If you get my meaning about what that is.
For $5 a minute.
Yeah, exactly. All right, so there we go. And there we go. Hey.
What's
So
about
it works
right?
in both directions. Or for any other rule that you might invent. Like the heap could be that one thing is the multiple of another or something. I don't know why you'd ever do that, but you could make up other rules. So this heap will go in either direction, min or max. That's it. Any questions on heaps? If not, you can have the rest of their time. It's still correct.
What?
It's not right.
Why, it's only a minute behind at the most.
Yeah.
I think it's getting closer and closer to absolutely correct. And then it's going to get further and further.
Let's
It
see how long
fluctuates
before it
regularly.
moves on. We gotta figure this out too.
It's consistently inconsistent. Sorry, I almost fell over.
No, you're good. Lean on me
Okay, let's wait.
when you're not strong.
Wait, hey, every 5 seconds it's advancing 5 seconds.
Wait, is that just how that clock works?
No, because it's
Apparently.
not at the right time. Yeah. Because the last time that I observed it and wrote it down, it was like getting faster. Like,
I know before, I've seen that thing just wig out. I don't-
yeah, because like one time we started and it read like 5:30 when we started, and then it was at like 9:40 when we ended.
Yeah,
And it was at 8:15.
Huh.
Clock may in fact be in the twilight zone.
Yeah, it's I think it's working.
Where's
now,
Jordan
though,
Peele when
in
we
its
need him?
own- It's working in its own way.
He's the host of the new Twilight.
Let's try it one more time.
Wait a minute, no,
That's
he's
its
making
own
it.
clock.
He's
All
making
right, so
it.
it's
That's
moving.
like-
Us. It's a very good movie.
3,
Huh?
4,
It's
5, and there it goes.
Us.
Yep, it is.
Those
Every
are
5 seconds, it's jumping
Correct.
forward 5
In
seconds,
the
which
game.
means it's keeping time now somehow.
What is wrong?
I don't know.
I guess nothing if it's working.
Well, yeah, that's just disconcerting.
Maybe it had
though.
a near-death experience. Some kind of epiphany.
It has a near-death experience.
It's like time's an illusion. That's what Einstein said. Time's a persistent illusion.
The most persistent illusion there is. Yeah, tell that to my lab due on Thursday, Einstein.
You could try that. Someone might
Believe me, I have.
Did you turn this lab in electronically?
Huh?
You turn this lab in electronically?
I haven't turned it in yet.
Well, if it's electronically, you can always try the. You can always try the corrupt the file strategy.
The correct file strategy.
Just put a bunch of black
Just go to
diamonds, question marks in there.
corruptthefile.com or whatever it is. It corrupts your file.
Are you? But how am I going to argue that if it's like stayed securely on PS11 the entire time? There are like no conversions in there.
Yeah, that would be suspect.
I could argue
I'm not-
regular expressions
I'm
error.
not saying that I've ever used this as hypothetical, but
Regular expressions error.
Yeah, I'll be like, Doc, I really messed my code up. I have to start almost from scratch.
Benjamin is not here.
but I do know something.
I work by myself now.
Corrupted like an entire semester worth of files and just got credit for.
This is from.
Oh, was it like a portfolio, like a huge portfolio due at the end of the semester, and you were just like, I don't know what happened, dog. There was one time that actually did happen on a flash drive of mine. I didn't know to eject the flash drive before you just yank it out of the computer. I mean, all the files it saved, but after a couple of times, there was some Photoshop and Illustrator documents it just wouldn't do.
Hey, it depends. If you don't have any files open and you just yank it out, sometimes it doesn't do anything.
Sometimes it doesn't do anything.
Yeah, well, if there's
Sometimes
nothing
it
open,
messes
if
up.
you're not reading anything from the drive,
Tell that to my Illustrator files.
Was the illustrator open and then you pulled it
I don't think so. But there was also one time I used to have that same MacBook Air, and I had attached to it a 1 terabyte hard drive that I taped to the back. And because it had like 60 gigabytes of RAM, and I needed World of Warcraft, and that's like 70 gigabytes. I'm sorry, not RAM.
I was gonna say 60
Sorry, storage.
Dang.
Storage.
60 gigs.
Overkill.
Yeah.
You could have so many tabs of Chrome open with that much RAM.
Dude, my laptop doesn't force quit Chrome anymore.
Actually, I think what is it? Like 64 gigs of RAM you can have on most motherboards. It's like 4 slots, right?
I don't know. Hey Doc, what's a core?
A core? So it's like an entire CPU, but it's on the same die with the other CPUs. So it's effectively the same thing as having multiple CPUs.
Okay.
And then you go. There's like the.
But how do
then
you
there's like the threads, which.
how do you calculate the processing power? Like from a four core CPU is not going to be twice as fast as a 2-core.
Only
Wait,
if it's
what?
utilized that way.
Huh?
So what it does is it provides for true multitasking. So like if you have, say, a 4-core processor, that means you can have 4 threads of operation that are really concurrent, not time-sharing concurrent like a multitasking operating system simulates. So that means that an operating system can schedule 4 threads that will run simultaneously, and that will speed up applications quite a lot. So it increases your total throughput. And if you write a program that can exploit it, if you write a program that uses parallel processing, then it can actually divvy a task up to those processors that work. That's how supercomputers work.
What?
That's how supercomputers work. Like if you were to go over to Oak Ridge and you were to look at Summit, you look at the clock speed of the individual processors, it's just a 3.5 gigahertz clock speed. But there's like 400,000 of them. So actually there's more than that. Because it's capable of something like 6 petaflops.
I was wondering, as far as data transmission protocols, we've gone from parallel to serial, right?
Yeah.
Could CPUs go through something similar?
Yeah,
Or
some
is it less
CPUs do serial. In fact, it used to be the case that sometimes CPUs would actually have serial registers. They do that as a cost saving measure. Like you could get, back in the 1960s, you could buy a PDP-8 that was the normal PDP-8, and it used parallel registers, and it cost, I think it was something like $65,000. And there was another one that used serial registers that was about, I want to say it was like $30,000. It was less than half of the price gone. And it was much slower though, because it had to shift the bits in time into its registers.
So just to clarify, more cores is better than fewer cores.
That is correct.
Okay.
Just a little random question. So, since we didn't get like another pair of programming today, would it be possible to make the one make it do Thursdays?
Well, no, we still have the one. I think. I don't.
My intention was that you'd finish it up tonight, but maybe I can let it slide till Thursday.
If you could, and also that would just be so dope.
That'd be really cool, you know.
We spent literally an hour and a half just discussing your code, your template.
All right. Yeah. So we'll say that so everyone, we're going to make the paired program due Thursday. But
Okay.
you're going to get another one for your same partner on Thursday as well. So if you don't finish it tonight, you don't have to panic. But still try to finish it tonight, because you'll want it. You want to try to have it finished when you come in on Thursday, so you'll be able to immediately start the next leg of the journey, which uses the code you're writing.
Can you explain the passing of the visit function? Also, there was no visit function in like the template or any of the stuff.
That's what I was gonna
Well, yeah, the visit function has to be provided by the user of the template.
Okay,
So
I was thinking that. Oh,
It's just like the code that we wrote tonight, where I passed in the function. So a function pointer, you just literally just put the function's name when you pass it in.
Okay.
So like you would do like in order, and then you would pass in the name of a function, like my visit could be the name of it.
Okay.
And you just put that in parentheses, but without the parentheses at the end of it to call it. Because you're passing a pointer to the function itself.
So it can use the function?
Exactly.
Okay.
So you're giving it the address of the function to use.
Okay. All right. Interesting.
You wanna?
Do it.
We wanna work on this a little more.
Yeah, I'm down.
And then, what do you have going on tomorrow?
What do I have going on tomorrow? I'm going to be at Pellissippi from 8:30 a.m. to 9:30 p.m. No, just kidding. Tomorrow's Wednesday.
Yeah.
I have the Spring Fling from 10:45 to about 1:45, and before that, I'm planning on being up at 7 a.m.
Okay, well here's, basically I have class get a class at 2 p.m.
Yeah.
And then they sent food. So
What's Wednesday? Yeah, I can do that.
So if you want to be like 2:30 or something.
2:30 tomorrow?
Yeah.
And
What
leave
is
now?
this stuff? I want to
That's possible.
go back.
I was gonna ask him one question because after we left, I went home and kind of tried to make the thing. I just don't
Oh, did you mess it up even more?
No. I
Yep.
just don't understand.
You've done some fresh new errors.
I just don't understand this one issue. I was gonna ask.
There's just one problem with it. I don't know.
You need to bring a thumb.
Why do I need to bring a thumb drive?
I kind of want to show you, but I don't want to show you.
Do you have something you need me to test run?
Huh?
Have something you need me to test run?
No.
What is it?
Oh, I don't know. I'll tell you later.
Hard.
Like, I feel like I want to share it because it's like, you're not supposed to share.
I feel you. Email it to me.
It's kind of like, like I could like discreetly like copy and paste it onto it right before. Because it's very hard for me to get this data, but I want to share it. I have to go to the Pirate Bay.
I thought that got shut down.
You can't like search for it and find it.
I feel you.
It's like
Does the
Very,
pirate actually exist?
Obscure.
no, not just obscure. I mean, it's very censored.
You have to.
Or is it some dank memes?
Yeah.
You have to-
Article 13.
Yeah, bank memes. It's a little harder to get.
You have to use Tor or something.
Yeah. He uses torrents for his memes.
No, I mean like you have to like use the onion router, you know.
That's a lot of memes.
Yeah.
Oh.
The
That's
best
what I'm going to
memes-
make my life work. I'm going to accumulate 2 terabytes of memes.
Do you have Reddit, right?
Oh yeah.
Okay. I was actually, you know how Article 13 is passed in the European Union? I was actually banned from the Dank Meme subreddit for being a suspected European user.
Ooh.
Whoa.
Yeah, I got a message for it and everything. I was really upset.
Did you message the moderator? Or did it come from
No, and it said
American?
don't message the mods because we're banning too many people to have an appeal system. I was like, what?
Well.
I got it. I was like, this has to be a joke. And then I tried
Oh,
posting.
it's April Fool's though, right?
No. This was like a week and a half. This
Oh.
is when Article 13 was passed. Despite the fact that apparently Article 13 doesn't go into effect until 2021 and also doesn't affect memes.
It's not
I can see
supposed to,
you
but
on
it
our
does.
programming.
Oh yeah,
Oh,
yeah,
yeah.
and also programmer dad jokes. Is one of my
Yeah,
other
I can
favorites.
see. I can see.
So I get exam quotes from the programming dad joke. I always put a quote on my final exams. Light.
I get happy when I can. When I see a new post on it.
See, what I did, like when I gave it to my uncle, I gave him.
That's right.
Like I'm letting him
That-
borrow
you'll
it.
get more and more of
I had to
those.
walk to his house. It's not that far. It's like 300 meters from where I live. So like walk to his. Well,
Do you use metric units?
Huh?
Do you use metric units?
It was like 300 yards, I guess.
Approximately 300 units.
Yeah, and I put it on his door. Like I taped it to his door to drive a little envelope. Because it's like, you know, you can't just put that stuff online. I don't want to track.
Heard.
Yeah.
Do you mind possibly if we could switch seats so that I can, for proximity
Yes.
to Brandon?
Yes. Okay, I'll do
Hey
that.
Brandon, are you in 1520?
Sure. Well, you are. Yeah, you are. Yeah, I'm in 15.
Oh, you're changing my seat. Like that?
Yeah, it's kind of your coat, man.
All right, man.
Have you done the webassign?
I'm doing that right when I get in.
Really?
Oh, wait, it's only like
Fire.
It's only like 5 questions.
We could collaborate.
We could. Hit me up on Discord. Discord.
Where's
Really?
my backpack?
Oh, it's right here.
Oh, thank you so much.
Well,
I'm gonna
well,
thumb
sorry.
drive next time.
I got you, buddy.
You're not gonna. Well, I mean.
So this is due Thursday, their program.
That is correct. Yeah. So we'll make it due Thursday.
But you should have it done by Thursday.
I would recommend having it done by Thursday because Thursday, you're
I don't
getting
know.
the next portion of this, which we'll use the code that you're writing.
Hey, your phone's here. Is it still?
That's like the first
Oh, you're still
step.
going?
Huh?
You're still going.
I am. What's up?